So yeah, I guess we'll get started. This whole exoplanetary like environmental storytelling thing is something I've been talking over with my advisor. It comes from there we go. So recently, some of my friends and fellow grad students have been obsessing over a game called Hollow Knight. Um, it's just like kind of like standard like platformer, like fantasy warrior game. You're a warrior exploring a fallen kingdom that's been struck by like a supernatural plague. The part of that that's relevant to this talk, the part that stuck with me is the way that the story is told. The characters in the game mostly speak in like gibberish. Really, the only way to learn about the world is through environmental storytelling. That's usually defined as the art of arranging a careful selection of like objects in the game world, so that they suggest a story to the player as they discover them. So every artifact, landscape, ambient detail, the music contributes to the narrative. I think that that's an interesting parallel to the kind of work that we do, like in the sense that we can't speak to the main characters of our research, can't ask a planet how it's doing, but there exists like a wealth of indirect information about planetary systems that we can use to inform our models. That's not like a new idea. I think that's like a core part of the human experience, and we've done a lot with the concept so far, especially when considering the environmental storytelling of our own solar system. That has resulted in like a very specific history from the Nice model that we can infer from the way things are arranged. So we're starting to see hints of that sort of environment of planetary systems is strongly connected to their properties. That maybe isn't a surprise considering that that's true for many other things in nature. But we've really only been able to make a study of it in the last decade, since Kepler. But without the specific granular information that we know about our own solar system, we have to speak in a more demographic sense. So I like to think that I'm in the third generation of exoplanet astronomers. You can probably lump all of 1995 to like 2009-ish, the launch of Kepler is like the first generation. For people in their early career, they were the ones finding out that planets existed, and they don't necessarily look like our own solar system. I think the second generation would be Sarah's generation from like 2009, the launch of Kepler, to like now-ish, where those early career researchers found out that not only do planets exist, but they're common, and they're so common, in fact, that we can learn things about them just from the sheer number of them. And I think I'm part of the third generation, which I think is starting about now. We're the ones that will learn about the individual characteristics of all kinds of planets and systems and put together like a coherent story with the tools we have available. So for me, that takes the form of taking some of what we learned in the second generation and testing the limits of those models that we built from the demographic information as we gather more information with our new and better tools. So with that said, I'll get to the first of my projects during the PhD, which is on the role of giant impacts. So as far as things that we've learned from exoplanet demographics, I think probably the most famous is the radius gap. This is a painstaking effort of a lot of people to drive radius uncertainties low enough that we could see structure in the period radius distribution. So the radius gap is the dip in planet currents at about 1.8 radii, 1.8 Earth radii. This is usually explained by core-powered mass loss or photoevaporation, sort of like after evolution effect, after the planets form. It probably represents the crossroads of a lot of processes, like both interior, those atmospheric processes, and also dynamical processes. helpful red arrow if you didn't. So those two mechanisms explain many features of planetary systems, but they cannot, however, explain them all. Um, so if you take a look at this figure, this has the planet density on the y-axis and the equilibrium temperature on the x-axis. You can see that planets and systems generally get denser as they get hotter and closer to the star, which reflects like losing their atmosphere. But some of these systems buck the trend in that there's like huge jumps in density between planets that don't necessarily make sense under the paradigm of core-powered mass loss or photoevaporation. And so this knowledge gap is where my first project comes in, and that's giant impact atmosphere erosion. So we only have this snapshot of planetary systems, like that we see from surveys like Kepler, and gathering information on formation of these planets comes from specifically how they're arranged. So by comparing like simulations to the planets that we see, we can see how the conditions that we put into our simulations might have actually shaped the planets that we see today. So let me describe what I mean by that. There are two distinct things that happen when forming a planet. When a forming planet is hit by another forming planet, you get atmosphere displacement from the shock wave. And so this is kind of like Newton's cradle toy, like the ball thing that goes back and forth. The impact energy will propagate through the planet, and that will liberate a substantial fraction of the atmosphere, like at the antipodal point by itself. So like the actual kinetic motion, and also the impact energy that goes into heating the planet. So here's like a schematic example of that. The actual thermal energy will kick off a period of rapid atmosphere loss through a process similar to the solar wind. So here in this plot, this is showing what on the y-axis, the ratio of impactor to target size, and on the x-axis, you have the amount of atmospheric mass liberated, and so like as the impactor size approaches the target size, you get closer and closer to all of the atmosphere being liberated by this impact. In order to build a model of how giant impacts impact the observed planetary population, what we need is a realistic population of planets that reproduce the planet population statistics that we have from Kepler. We need to know whether or not a particular planet experiences a giant impact and when or how often it happens, which is pretty much random, meaning that we can't just generate systems from the distribution of various planet properties. We have to actually simulate this. Problem with that is in-body simulations are expensive in terms of both compute resources and the amount of PhD that you have to spend on it. We also need to observe them, like with the same biases that we got from Kepler or TESS, in order to accurately infer what's going on. And so what I did was take simulations that had already been done in Dawson et al. 2016, and basically apply this giant impact formalism on top of it. So the key feature of these simulations is that they reproduce the Kepler dichotomy. So the fraction of stars where Kepler saw only one transiting planet is far too high for most of the planets to be coplanar like they are in our own solar system or in the same. So the systems we see must be predominantly dynamically hot. So that means that their inclinations and eccentricities are like higher than they would be for a multi-transiting system, which were dynamically cool. And so the differences in the simulations I used, there are two sets. One set that produces dynamically hot planets and one set that produces but on the slide. And so we also need to build a model for the giant impacts. So we need to do this for both planet populations. And we need to show the difference between what happens when you have giant impacts on and what happens when you have giant impacts off. And also compare that to what would happen if photo evaporation was actually the only operative effect. So to do that, I used vPlanet, a whole bunch of different codes for planetary system evolution, and one of them is atmospheric escape. Came in very handy. And so I had all the planets accrete an atmosphere, which is about 5% of the mass of the planet core. And then they all get subjected to 5 billion years of atmosphere loss driven by the host star. And planets that lose 90% of their envelope, I just put those in the bin that they've lost their atmosphere. For giant impacts, though, the median impact energy is actually much more than you need to liberate the atmosphere from any of these planets. So these are like Earths combining into super Earths to kind of provide a scale for that. So basically what I did is if you have one impact, then you've probably lost the whole atmosphere. So this is an example of some of the systems. So on the left, you have the multi-transiting system, so dynamically cool. You have a bunch of planets that are very coplanar. And on the right, you have the singles where they're much less coplanar. So using vPlanet, I simulated actually, let me back up. So first, we have to see which planets transit. So these would be the planets in green here. You can see in the multis, you get to see a lot more of the planets transit. So using vPlanet, simulated how many of these planets lose their atmospheres to photoevaporation. And using the model I mentioned before, this is vPlanet, losing atmospheres to photoevaporation, but I also used the model of them losing their atmospheres to giant impacts. If you look at their losses to photoevaporation, it's kind of predictable, like the closest planets atmospheres. For giant impacts, that is not always the case. Since giant impacts are stochastic, like it's basically random which one of these planets lose their atmosphere. And so what you get, go ahead. Yes. And so I did photoevaporation on, photoevaporation off. You get like the maximum distance. Enter. So when you do this, you get divergent outcomes. So giant impacts on the left and photoevaporation on the right. In teal are the planets where the atmosphere outcomes were roughly the same. So they either kept their atmospheres or they didn't. In both sets of simulations. The yellow and purple ends that there were a different outcome for both simulations. So it appears that low density planets, which are either fairly high mass and hot and puffy, or low mass and on the edge of losing their atmosphere to ballistic escape, form one population. You have a population of high density remnant cores, which lost their atmospheres to giant impacts. You have low density, high mass planets, which are just resistant to photoevaporation, so those are like closer to being giants. And you have partially photoevaporated. And so this is a plot of that population. This is for photoevaporation. If you look at the marginal plot, or just like 2D plot, you can see that you don't see any planets at all in the radius gap. part of that is an artifact of like the kind of crude way that I've done this. There's a lot of difference between stars and their like X-ray and UV histories, and just difference between stellar types that will sort of fill in the radius gap at some level. But I think what I'm referring here is that the radius gap should be pretty empty if photoevaporation is the only operative thing. If you look at this for giant impacts, the radius gap is much more full. And I think a natural question is, what are these planets? Like, if you go look, are we able to distinguish them from other planets? Like from the previous slides, we know that they have like different like mass and radius or density characteristics, but you would also expect them to be dynamically distinct. There should be some dynamical evidence of a giant impact if that's indeed what happened. So using these same simulations, I actually checked out if anything in their orbital parameters stood out for planets specifically in the radius gap, as that's like our kind of high leverage population of planets, and something sure did. So these plots are the eccentricities and mutual inclinations on the y-axis versus the radius of the planets in both the single and multi-producing simulations. So on the left, in both panels are the singles, and they're generally much dynamically hotter, which leads to like kind of fuzzed out, much more uniform distribution in this space. Multis, they should all be dynamically cool. That's definitionally what these simulations produce. And that's true except for planets as they get close to the radius gap. They are systematically more inclined, more eccentric, and more widely spaced than their neighboring planets. I didn't put the mutual Hill separation one on here and have you able to see, but it also looks like this. And so those are all things that one might expect if a planet has had a giant collision with a neighbor. And so I think it's interesting that the same phenomenon, giant impacts, can imprint as both an atmospheric loss and an increase in dynamical temperature. So this is all coming from a model of giant impacts, an atmosphere loss that is kind of crude. So this kind of went on the back burner while I did other projects. So imagine my surprise when at Extreme Solar Systems, Greg Gilbert gave a talk that indicates that planets in the radius gap do actually have a higher eccentricity than planets that aren't in the radius gap. And this isn't easily explainable with presently favored photoevaporation or core-powered mass loss pathways. Giant impacts offer like a natural explanation. I really hope this paper comes out soon. So at this point, I have gotten completely sidetracked from what my original thesis plan was. But that seems good because this line of inquiry seems like it's producing results, which brings me to the next section, the breakdown of peas in a pod. And so to explain shortly, the peas in a pod phenomenon is when that neighboring planets seem much more similar to each other than just random chance would dictate. There are a lot of like energy reasons that this maybe should be the case. And I think there's been like a considerable back and forth over whether it's an observational effect, and at least some of it isn't. So I think I'm pretty confident in saying that this effect exists. There's been a lot of poking and prodding at it already. And I don't think it's quite settled yet, but I think most importantly for what I want to do is that the fact that there's an observable peak at one end of the radius ratio of planets. And because it's so clear, you might expect that any like subsample of planets, any R, would produce sort of the same radius distribution, or at least look similar. I'm going to bring this slide back because I'm a bad writer and the distinction between foreshadowing and lampshading is lost upon me. So understand that when you have a hammer, everything starts looking like a nail, but that won't stop me from hammering home the point that giant impacts can also be responsible for deviations from orderly formation. Um, yeah, I really want to underline this, like systems that have planets of ambiguous compositions, like the weird density things that we saw in the previous slides. It should also have unusual size ordering characteristics. So going back to the radius ratio distribution, as a first pass, I just kind of downloaded the data from the Exoplanetary archive, which I think every one of us is guilty to see if planets in the radius gap show any differences. And so when you compare them to the whole sample in purple, the green plot here is the ones that are in the radius gap, or at least the naive radius gap. You do see kind of a lack of planets at 1. So I showed this to Sarah, my advisor. She's like, "That's great, but you can't just download data from the Exoplanetary archive." So we went back for a more careful sample selection. So I started using the Berger 2023 planet radii for a more homogeneous sample. Then I cut that sample down to planets that have a radius error of less than 0.1 R-Earth. So you can reasonably locate this in the radius gap, which is about that wide. Then I used a radius gap described in that paper, which is kind of like a piecewise function in stellar mass of where the radius gap is to select my planets that are in the radius gap. And this leaves me with only a few planets, but I'm pretty sure that these are in the radius gap. So because I only have 15 planets bootstrapped to make sure this isn't just a small number statistics thing. And so after doing that, I arrived at this. So systems with a planet in the radius gap, so that would be up in the top right corner, have far fewer neighboring planets that look like twins. So you can see that instead of having a peak at 1, the peak is shifted quite far away from 1, and there's in fact a drop down to very few planets at 1. If you shift the definition of the radius gap up or down a little, which is what I've done in the other 3 panels of this, it goes back to looking broadly like the parent distribution. I think that is a key thing. Actually depends on planet, something physical is happening. Actually depends on whether or not planets are 1.8 Earth radii. So what I'm taking away from this is that planets in the radius gap seem to signal some change in their system. It's like putting a Panera Bread in the neighborhood, things start to change a little bit after that. So combined with the first part of this talk, I think that this is compelling evidence that something weird is going on with the radius gap, and it's probably related to dynamics. So now we're going to have a whole whiplash thing and go to my other project that I work on. It's sort of similar in the vein that I'm still prodding at something that we've discovered from the second generation of it. But in this case, instead of the dynamics, well, I guess it is still the dynamics of planetary systems, looking at the limit of where binary suppression becomes a factor. So we know that planets exist in binaries and even in close ones. One way that we've learned about them is through Gaia observations of co-moving companions, which has the advantage of being widely applicable, but it's mostly sensitive to wide companions. We've learned about close binaries hosting planets through transit surveys, which have found planets orbiting the binary, orbiting one star in the binary. But those are relatively rare. So if we want to learn about things in the demographics, then it's hard to do that from circumbinary planets. We need more information on the population of binary hosts. And so we've traditionally, in the 2010s, turned to adaptive optics, and then lately have gone to Gaia for that sort of survey thing. But again, when you have something like adaptive optics, how far away you are depends. Changes how close of a companion you can see. And for the Kepler planets, it's not very close. And despite that, we've learned that planet hosts that are binaries suppress planet formation in both of these papers. So across 2016, you can see that the distribution of projected separations for stars that have planets versus stars that don't is different. And the Moe and Crowder result, they actually like kind of quantified like what the suppression effect is for the occurrence of planets, and it goes down by like a factor of 10 by the time you get to 10 AU. And so I think since most stars are in binaries, it's a really important thing for us to understand if we want to understand the population of planets in the Milky Way. I want to say that like all these ideas are sort of linked together. Binarity informs whether and how planetary systems form at all, as we just saw from those results. But the presence of a binary also seems to affect whether the radius gap even exists. And so I'm not simply like drawing red string between things on like a whiteboard. And so I guess what I've done for this project, I guess, is the most basic part, is how do we detect binaries? As I described before, it's not like a simple task, particularly when a lot of our stars of interest, stars that we know that there are planets around, are far away. And so for that, I've used Gaia. That will never work in my lifetime, I guess. So here is basically a plot of the RVs of a binary on the top, a quiet star, and this convolved with like the Gaia uncertainty on radial velocity. I think you could probably pretty easily tell like that the top one has a binary if you had all of these measurements, but unfortunately, it does not have all of those measurements. You'll get 20 plus or minus like 10 for most stars in the Gaia RV catalog. And that's for the Gaia team itself and maybe in DR4. Right now, all we get is the median RV and error. Really, the only difference in these sets of information is the size of the error bar. The one that we know has the containment is much noisier. And so you can actually take that information, so see if a star is a binary, and as far as how you do that, you start with a statement that there is like some distribution of stellar RV noise. Some of it is intrinsic, some of it comes from your measurement, some amount of it is due to companions. Now, if we assume that the intrinsic noise is just noise, it could be normally distributed. We also assume that stars that are close in color and magnitude, high position, have similar RV error bars. That isn't strictly true, obviously. There would be any number of things that are wrong with that statement, but this ends up just really being some sort of outlier statistic. And so it's true enough for a normal main sequence star in the absence of some systematic. So on the right, this is like the idealized case. So according to our assumptions, our RV noise, so that's on the x-axis, could belong to a chi-square distribution when you square in summit. So this is an example case of just single stars with their own Gaussian noise plus the measurement error from Gaia. So if you contrast that with this blue histogram, this is simulating binary stars with the Gaussian noise plus measurement error plus a periodic RV signal. And so if the RV error is like way out in the tails of this distribution, it's likely not just noise, and that's basically the entire like conceit behind this idea. So I think this formalism is important. We've previously tried to do this using a mixture model, but that makes it hard to understand like what your error means. That is like the critical exercise here. So using this formation, usually this formalism enables us to have like a p-value, so we can actually like assign a p-value to how likely we think it is that this is a single star. And so this comes with a few caveats. So for one, the values that we infer from for our sigma for our injected noise is itself kind of noisy, because I think this should probably be a thing that Gaia gives you. They don't. So we do the inference, try to offset it by Five randomly selected 1,000-star bins. And then we average the estimates of the sigma for bins with more than 100 targets, so trying to like keep any weird effects from weird stars down. And so if we smooth that out, we can make a measure. We can make this plot of the per measurement transit uncertainty. So this is like the RV uncertainty that you would expect for any Gaia star in the color and magnitude space. And so we can see that Gaia can actually get down to sub-kilometer a second noise for bright targets, which is really cool and will come in handy later. And so we can make a map of the parameter space where this method is sensitive using simulated RVs, the real error distribution from the stars that go into the model. And so we recover most main sequence binaries with separation of less than a few AU. There's a little like black corner up there because Gaia culls things with RV errors of greater than 40 kilometers a second from the RV catalog. I think they put most of those in the non-single star catalog, but since we don't have the data, we can't infer anything. And so this is basically the recovery rate as a function of mass ratio on the y-axis with separation on the x-axis, and the magnitude limits by the contours. But each of these contours, like we detect 99% of things like within it. So our detection efficiency is great for main sequence binaries, but as you get closer to the Brandorf limit, it starts to drop off. And for redder stars, it gets worse, which follows how our per transit RV uncertainty works. I want to emphasize that you can use this for your forward modeling. Like if you ever have a reason to wonder about binaries in your sample of whatever, it's quite straightforward to use code. It's called paired to generate a population of radial velocity binaries and then see what gets detected by Gaia. Since we know that the fraction of binaries recovered is a function of per transit measurement uncertainty and the number of measurements and how they relate to one another, we can build like an RV orbit model and compute the probability density for the actual measure RV semi-amplitude, which is conditioned on like a set of number of noisy observations. This is really computationally expensive, but it works. So basically that means for anything that we have a Gaia RV for, we can estimate what the semi-amplitude of that was despite not having the actual RV measurements. I want to highlight that a lot of similar work has been done for RUI. I think a lot of people really like to use RUI, especially for exoplanets, but RUI is sensitive to like a totally different parameter space than paired is. RUI is much more sensitive to wide binaries, and paired is much more sensitive to binaries within 10 AU. So I'm sure that that explanation was very convincing, but I think knowing like how this applies to real world data will be much more convincing. So in blue is a histogram of the p-values of a population of stars that I won't name yet, where 0 is the highest probability of being a binary. So this would be an approximately uniform distribution if stars only had Gaussian RV noise. Now, if we overlay applied orange, another population that I want to without knowing anything else about these two populations, you could safely conclude that one is mostly, if not completely, composed of binaries. And you would be correct for doing so. This is the whole Kepler input catalog just run through paired, which has about 67% coverage, and the Kepler eclipsing binary catalog, which is about the same. So these are relatively short period edge-on binaries, like ones that we should have no problem detecting if paired works, even if they are on the nib side. And so nearly 75% of these stars are flagged as binaries without ever having to look at like a light curve or actually go out and take RV measurements. Similarly, we conducted a bunch of tests where we compared Gaia's non-single star catalog to paired, and we come from the same spacecraft, so we better get the same answer. And so this is a plot of the Gaia non-single star catalogs, P1s, so they're single line spectroscopic binaries. We recover more than 95% of them just from the RV error behavior, whereas this is populated by the actual like RV epic measurements from Gaia. And so here's a color magnitude diagram of our sources. So on the left, the color bar represents the mean p-value in each bin. So in the insets, you can see like the difference between the p-value distribution for regions where we expect there to be mostly binary, so like on the binary main sequence on the right there, and where you expect there to be less binary, so like right in the middle of the main sequence in the left inset. On the right, the color bar indicates the fraction of sources in the bin that we consider to be binaries, and I think this tracks pretty well with how we think binaries are spread over the color magnitude diagram. So getting all this for free is like pretty good in my book, but we have to test if we could like robustly recover the correct answers if we injected them. So there are a few levels we can test this on. The first is on simulated RV data. Like I mentioned before, you can't just simulate RV data and run it through. So I used the same pink binary stars from a few slides ago, and I've given them per measurement uncertainties directly from DR3. And the size of the circles indicate that uncertainty. You can see whether we recover the correct semi-amplitude mostly depends on how uncertain we are about the RV noise of similar looking stars. So that basically means for stars where we have a lot of examples, we do better for. Stars where we have few examples, we do worse for, which should make sense. And the remaining non-random scatter actually depends on the eccentricity of the binary orbit. So I guess the next step would be another Gaia-to-Gaia comparison. Gaia also has RV measures they published that have a similar p-value. They only do this for 6 million stars, whereas we do it for 31 million. But again, this is from the two-body orbit sample where they actually have directly measured the RV of these binary stars. And so that's on the x-axis, and on the y-axis is our inferred RV semi-amplitude. You can see that there's like pretty tight agreement considering that we're just using one number. I think the test that was most convincing for me personally was using something like SB9, which is like a mid-resolution RV survey for a bunch of the binary stars. And so this is for all the stars where we have overlap with them. You can see that actual like ground measured semi-amplitudes we track with really well. So most of the time this has been cited, which is 4 times up now, in stars people. I originally produced it for planet stuff, and so I'm currently working on this paper, but I'm trying to look at the suppression effect of these close binaries, and this is just a preliminary plot, but in purple we have like just the p-values of the kick plotted. In black is what it would be if it was just Gaussian noise only, and in green is for the KOIs. You can see that the KOIs seem to be much less likely to be binaries, even past the point where we're comfortable declaring something as a binary, which I think the actual shape of that distribution between like the red dotted line and the black one will tell us a lot about what kind of systems these are actually in. But this is just something I'm excited to be working on right now. And I think I'm getting close to time, so and stop for questions.
Have a quick one? Yeah. Awesome talk. Really, really cool work that you're doing. Just a question, I'm not familiar with those RV measurements you're taking, but on those plots where you're showing the two, it was early on in that section, where you're showing the two signals of binary versus non. Yes, these ones, that's perfect. I was just curious, what's the double peak, or kind of little tiny peak, in both populations there?
So this distribution has like a peak, and I think when I generated this, hold on, I have to like dredge this back up.
No, you're good, you're good.
They're like, I generated and it embeds. If you don't do it finely enough, like they're like peaks based on the RV jitter. You end up having like a bunch of these distributions sort of superimposed on one another.
Okay.
Does that answer your question?
So it's just like an artifact of having like a different distribution going into this combined one?
Yeah.
Okay. Cool, thank you.
Thanks a lot for the talk. That was great. I'm just curious about the collision stuff, the impact collisions for the beginning. And I guess I'm just curious about the effect of time on that. You know, you're comparing the collisions to photoevaporation, and photoevaporation happens over, you know, long periods of time, whereas collisions are more so. So yeah, I'm just curious, like, how does the time at which the collision happens maybe impact the loss of the atmosphere?
So in modeling this, they model when the gas dissipates, and basically after the gas dissipates, I assume that you can't replenish your atmosphere anymore, so any collision after that will strip your atmosphere. And you're right, that happens on like 5 million-ish year timescales, which is much shorter than the photoevaporation one. But most collisions seem to happen like within a few million years of the gas dissipating, and then things calm down.
I have a follow-up to that one. So in a few more plots, I think you showed the eccentricity and the back one. So the planets, am I reading this right? The planets around the radius gap are more likely to be hotter, like dynamically hotter here?
Yes.
So could it be evidence then that just they're not transiting? Like they're at higher inclinations, they're less likely to be caught transiting. Could it be, you know, how much of that could just be an observational effect?
So this is using like the intrinsic planet itself, so I haven't selected for things that transit here. When you select for things that transit, this effect is a lot smaller. Like you can maybe tell at the one signal level that they're hotter, but for the most part, they're not transiting anymore, so you're just missing them.
Yeah, I mean, if there are, I guess my question is there a lack of planets in the radius gap, or are they just, we're less likely to observe planets because they are dynamically hotter?
Good question. I think yes, we're definitely less likely to observe them, but I don't have a good sense for like how much less likely.
Or yeah, I guess, yeah, maybe it's another question of, does photoevaporation contribute more, or does dynamics contribute more?
Thanks. Yeah, going, I guess, back towards the end, your KOI plot. KOI is like Kepler objects of interest. That's like the planets, right?
So the distinction is only confirmed KOIs.
And then I don't know what KIC stands for. That's
the Kepler input.
Oh, okay, so it's systems with planets and systems without planets.
Systems that include systems with planets, but mostly don't have transiting planets.
Okay. Mhm.
Yes, KOIs, and so this is just a confirmed planet sample out of the KOI, so your stars could definitely host planets.
Cool. Hey, Quadry, great talk. I just had a general question about the whole like peas in the pod phenomenon, where I was curious as to what sorts of characteristics are people looking at when you're sort of assessing like their similarities? Is it like their atmospheres that are similar, or different planetary properties that they're comparing between the two, or multiple planets?
People mostly look at their radii, like,
Okay, yeah.
because it stands out when you look at like a family portrait of a system, like the planets are
Yeah.
all close to the same radii.
Okay.
There is like an effect in mass, but I think it is less pronounced. And this is also like a very active area of research, but it's basically mostly just planet radius.
Gotcha.
Any other questions for Quadry? Were there any online? I didn't look.
I don't think so. It would have popped up on. Thank you.
Quadry, a round of applause. He is occupying the spare desk in my office, S321. If you want to meet with him, there's a sign-up sheet. Otherwise, thank you, Quadry. And I guess lunch is next.
I was saying that if people are interested, right now we're doing Goddard on the Green, which is just a short walk away. That's also probably where a lot of folks are right now. But if anyone wants to come with us, I think if you're down, we could walk over there. There's like food trucks and stuff like that, and there's horses apparently. Yeah, the map says horses. I don't know what the horses are doing, but if anyone wants to check them out, feel free.
Horsing around.
Yeah, you could just watch them.